Planet Semicon welcomes you to explore the field of semiconductor physics and technology, the foundation of microelectronics and VLSI design engineering.
This Part 4 STA presentation provides an overview of static timing analysis through the study of a typical timing path. We will examine the concepts of timing slack evaluation by slack graph method. Also introduced to a typical STA tool, timing report that presents the evaluated data. Finally, we will discuss common timing violations and the techniques used to achieve timing closure. So, let's get started. The reg-to-reg path begins when data launches from the first flip-flop at the active clock edge. This data then travels through the combinational logic and interconnect delays toward the second flip-flop. For correct capture, the data must arrive before the next clock edge minus the setup time requirement. Setup time is the minimum interval the data must be stable before the capturing clock edge. If the data arrives too late, a setup violation occurs and the flip-flop may latch incorrect values. Designers analyze the arrival time against the required time to calculate slack. Ensuring positive slack confirms that the setup time constraint is satisfied for reliable operation. Two flip-flops FF1 and FF2 connected in sequence, through combinational logic and interconnect delay. The outputs Q1, Q2, and the inputs D1, D2, represent the data flow path between the flip-flops. The timing diagram illustrates the clock and the data waveforms, highlighting how signals propagate through the circuit. Important delays, such as clock-to-Q, combinational, net delays and arrival times indicate the data. The shaded regions indicate the hold time windows around the clock edge, emphasizing the critical timing requirements. Vertical dashed lines mark the boundaries within which data must remain stable to ensure correct capture. Altogether, the figure demonstrates how hold constraints govern reliable data transfer between sequential elements in synchronous digital design. The slack graph method is a principal implementation in static timing analysis. It begins by plotting required arrival time and actual arrival time across nodes. Slack is defined as RAT minus AAT, showing margin at each point. Positive slack indicates timing safety, while negative slack highlights violations. Forward and backward graph traversals are superimposed to capture path delays. This visualization helps identify critical paths and dominant delay contributors. Thus, the slack graph becomes a powerful tool for timing debug and closure methodology. The slack graph method starts by identifying the timing path and its launch and capture points. The launch clock edge defines when data propagation starts through delay elements. Actual arrival time is computed by summing clock-to-Q, logic, and interconnect delays. Required arrival time is set using clock period, setup, skew, and uncertainty. By superimposing the RAT graph over the AAT graph, the difference between at every node the slack of the timing path is computed. Based on the results, optimization violation fixing is carried out. This timing path illustrates a register-to-register data transfer analyzed using static timing analysis with the slack graph method. The forward slack graph begins at the primary inputs and launch flip-flops, where initial arrival times are defined, such as the 0.1 ns starting point. As signals propagate through each logic gate, incremental delays are added, producing cumulative arrival times at every node. The annotated values in red represent the computed arrival time at each stage based on gate and interconnect delays. Multiple converging paths are resolved by selecting the maximum arrival time, ensuring worst-case timing is captured. This propagation continues through intermediate nodes, clearly showing delay buildup across the timing arc. At the capture flip-flop inputs, the final arrival time reflects the total path delay from launch to endpoint. This forward traversal forms the basis for slack computation when compared later with required arrival times. The required arrival time computation starts from the capture flip-flops, defined here by the setup constraint with trek equals 1.5 ns. This required time is propagated backward through the combinational logic toward the launch side. At each stage, gate and interconnect delays are subtracted, reducing the required time at preceding nodes. For reconvergent paths, the minimum of the incoming required times is selected to enforce the most restrictive constraint. As the backward traversal continues, values reduce from around 1.5 ns to 1.4 ns, 1.25 ns, and further toward earlier stages. This process ensures that every node reflects the latest allowable arrival time without violating setup requirements. The final RAT at the launch flip-flop defines the timing budget, enabling slack computation when compared with AAT. At the primary input, slack is 0.0, showing perfect alignment of required and arrival times. At the first gate node, slack drops to 0.05, a small violation that begins to erode margin. Deeper in the logic path, slack worsens to 0.055, marking a clear timing failure. At the output stage, slack recovers to plus 0.20, giving margin and robust operation. Positive slack values like plus 0.20 mean signals arrive earlier than required, ensuring safe synchronous performance. Negative slack values like 0.05 and 0.055 mean signals miss the required window, limiting frequency and reliability. The resultant RAT-AAT graph highlights these safe and unsafe nodes, defining the true critical path. In the design shown, the reg-to-reg path begins at the output of the first flip-flop, FD1, triggered by the clock edge. The signal propagates through the intervening combinational logic, passing through the inverter and NAND stages, each contributing its own delay. The arrival time at the input of the second flip-flop, FD2, is then evaluated against the required time window defined by the clock period and setup constraints. As shown in subsequent slides, the STA tool extracts data on path information, path delay, the AAT, path requirements, the RAT, and the summary that presents the computed slack, indicating the violation status. Let us go through each of the timing verification processing steps involved. The path information section of an STA report identifies the exact timing path being analyzed and serves as the starting point for timing debug. It specifies the start point, where data is launched, and the end point, where the data is captured or observed. The report also indicates the path type, showing whether a setup or hold timing check is being performed. In addition, the path group identifies the clock domain or timing group to which the path belongs. These details help designers understand the source and destination of the timing path, the associated clock relationship, and the nature of the timing analysis. By correctly interpreting this information, engineers can focus their timing closure efforts on the appropriate portion of the design. The clock CLK1 begins at the rising edge with 0 delay. Input external delay contributes 2 nanoseconds to the path. Data enters at node data 1 and propagates through the inverter U2, adding 1.54 nanoseconds. It then passes through NAND gate U12, increasing delay by 0.98 nanoseconds. Next, NAND gate U23 adds 0.66 nanoseconds to the timing path. Finally, the signal reaches the flip-flop input prism_reg1/D, with an additional 0.81 nanoseconds. The total data arrival time accumulates to 5.99 nanoseconds, defining the critical path delay. The clock CLK1 begins at the rising edge with a time of 20 nanoseconds. The clock network delay is considered ideal, adding no extra delay. At this point, The flip-flop clock pin prism_reg1/CP aligns with the same 20 nanoseconds. The library setup time requirement subtracts 0.80 nanoseconds from this reference. This adjustment shifts the required arrival time to 19.20 nanoseconds. Thus, the data must be stable at the input before this required time. Together, these values define the setup timing check for the register in static timing analysis. The data required time is set at 19.20 nanoseconds. The data arrival time is measured at 5.99 nanoseconds earlier, shown as negative. Slack is calculated as the difference between required and arrival times. Here, the slack value is positive at 13.21 nanoseconds. A positive slack indicates the timing requirement is comfortably met. This means the data arrives well before the setup deadline. The path therefore satisfies STA checks, ensuring reliable operation. Timing debug is the systematic process in static timing analysis to identify and fix violations. When STA reports negative slack, designers analyze the failure and apply suitable optimizations. The first step is to locate the critical path showing the worst negative slack. This path is studied for clock delay, logic delay, interconnect delay, fan-out, and loading effects. Setup and hold violations are examined separately, since each requires different fixes. Reports are checked for dominant delay elements, constraints, false paths, and clock definitions. Finally, optimization techniques are applied and STA is rerun. This iterative cycle achieves timing closure. Gate sizing replaces slower gates with higher drive cells, cutting down propagation delay. Buffer insertion strengthens signals by adding buffers, reducing delay across long nets. Logic optimization restructures or simplifies combinational logic, lowering logic depth. Pipelining introduces extra flip-flops, breaking long paths into shorter stages. Redimming shifts registers across logic, balancing delays between paths. Routing optimization shortens interconnects, minimizing parasitic resistance and capacitance. Clock skew optimization adjusts clock arrival times, improving setup margins. Cell swapping exchanges high-threshold cells for faster low-threshold ones. Reducing fan-out splits heavy loads with buffers or replicated drivers. Finally, constraint optimization refines timing constraints, eliminating unrealistic path analysis. The basic effort in hold optimization is to increase the delay, so that hold window time is satisfied. Following are various methods adopted in fixing hold violation. Delay buffer insertion is used to intentionally slow down fast data paths. Increasing routing delay by lengthening interconnects adds extra propagation time. Downsizing gates replaces faster cells with slower drive strength versions to reduce speed. Clock skew adjustment delays the capture clock or advances the launch clock to improve hold margins. Adding delay cells introduces dedicated elements designed for hold time correction. Increasing logic depth by inserting small logic stages further raises propagation delay. Together, these methods ensure that data remains stable long enough to satisfy hold time requirements in synchronous circuits. In this presentation, we have reviewed the key concepts of static timing analysis, including timing paths, timing constraints, slack evaluation, timing verification, and timing closure techniques. These topics provide a foundational understanding of how timing correctness is ensured in modern VLSI designs. The material presented has been compiled from technical literature, educational resources, industry documentation, and publicly available online references for learning purposes. While the subject is extensive, this overview aims to provide to a beginner a practical starting point for understanding STA methodology. Hope the concepts discussed will be helpful in interpreting timing reports and working with STA tools in real design environments. Thanks for your time. Hope this presentation has provided STA basics, required for appreciating the significance of timing analysis in the VLSI design. Thanking you once again and hope to meet you in the upcoming video. Bye for now.